Hey guys, hello, welcome back. Today we are going to be covering equations, inequalities, and graphs in one shot. Okay, basically what this chapter is about, it has modulus inequalities, it has the graphs of cubic equations, the modulus graphs of cubic equations, and certain equations which look complicated but can be actually simplified into a quadratic equation using substitution. Okay, so some of them are quite simple concepts, but some of them can be quite tricky, and there are a few things which you should keep in mind. Okay, so we'll cover all the details about that. So yeah, let's get started. Okay, without any delay. Now, the first thing is modulus inequalities. Okay, so you remember what a modulus is? Okay, if you don't remember the modulus, then you can look at my video on chapter 1 on functions. But if you just want a very brief recap, modulus is something, it makes anything inside it positive. So if you have modulus of -5, it becomes +5. If you have negative modulus of 5, however, that becomes -5 because the negative is outside the modulus. If you have negative modulus of -5, again, this becomes -5 because this inside is +5. So negative of +5 is -5. Okay, then we cover how you can solve modulus equations. For example, if modulus 3x plus 5 is equal to 2, this 3x plus 5 could either have been 2 or could have been -2. Because after the modulus, it became 2, right? How do you know before the modulus it was 2 or -2? So then you can solve it like this. In different cases, then you can find the value of x and then you can solve this. Okay. Now we're going to extend that idea further into equations which have a modulus on both sides. Okay. Into equations which have a modulus on both sides. So let me actually get a nice example for you. And that example will have a modulus on both sides which are with a equals to. Okay, it's modulus on both sides with a equals to. So I have an example. Modulus of x minus 5 is equal to the modulus of x plus 1. Okay, now the basic idea which you have to do here is that you square both sides. You square both sides. The thing is, because you don't know if the modulus was, if without the modulus it was positive or negative, right? But if you square anything, even if you square a negative number, it becomes positive, right? When you don't know if it was positive or negative, and you can't do it by case, really. I mean, I will be honest, you can do it by case. Okay, there are two ways to do it. The first way is to square both sides. By squaring both sides, what you're doing is, because it could have been negative, the modulus could have been negative, it could have been positive. But if you square both sides, it will be positive no matter what. So you have eliminated that constraint. So if you do x minus 5 square equals to x plus 1 square, then it becomes x square minus 10x plus 25 is equal to x square plus 2x plus 1. Then you can do some maths. It becomes 12x equals to 24 and x equals to 2. You can try substituting it inside. Modulus of 2 minus 5 is 3. Modulus of 2 plus 1 is also 3. So yeah, x equals to 2 is correct. So x equals to 2 is our answer. Okay. There is one more way we can do it. Okay. Remember how modulus of x minus 5 was equal to 2? We did x minus 5 equals to 2. X minus 5 equals to -2 because you don't know which one is positive, which one is negative. So in this case, when you have modulus of x minus 5 equals to modulus of x plus 1, actually there are 4 cases. This is positive, this is negative, this is positive, or this is negative. Okay, because there's a modulus there. If you don't know if inside is positive or negative, right? So when you remove the modulus, it could have either been positive 2 or negative 2. So it could have either been positive x minus 5 or the negative of x minus 5. So let's consider case 1 where where the first one's positive. Okay, where both are positive. Okay, let's consider the first one where both are positive. So that will become x minus 5 is equal to x plus 1. Let's consider the second one in which the first one's positive, the second one's negative. So it becomes x minus 5 is equal to negative of x plus 1. Negative will be to the whole thing. Okay, then the first one's negative and the second one's positive. It becomes negative of x minus 5 is equal to x plus 1. Then the fourth case is both are negative. So it becomes negative of x minus 5 is equal to negative of x plus 1. Now notice, these two things are essentially the same, the first and the fourth one, because the negative and negative can cancel. And these two things are also essentially the same because you can move one negative from one side to the other side. You can move one negative from one side to the other side. You get it, right? You can multiply both sides by negative and it stays the same. Okay, so essentially what you have is almost like the same thing. You can get x minus 5 is equal to positive x plus 1, or x minus 5 is equal to negative of x plus 1, just how you would do with any normal equation. Okay, but here's the problem. If you solve this, you will get, well, 1 equals to negative 5. So there's nothing like that. So there's no solutions in this one. And this one, it'll give you x minus 5 is equal to minus x minus 1, which becomes 2x equals to 4 and x equals to 2. So you can see we are getting two equations as in this case, but only one of them is giving us the answer. The other one is giving us 1 equals to negative 5. So just no solutions there. Okay, just no solutions there. So this is another method which you can adopt. But one warning which I might want to give you for squaring both sides, right? Always check your answer at the end. Always check your answer at the end, because you might get an extra answer when you square both sides. There are chances you get an extra answer when you square both sides. Let's see why that is. For example, suppose x equals to 7. Okay, suppose it's given. Suppose it's given that x equals to 7 for some equation. Suppose, although you already know x, suppose you want to square it. Okay, it becomes x squared equals to 49 already then. So now want to find x, let's square root it back, right? But now it will be plus minus 7. Because when it's x squared equals to 49, because negative 7 squared is also 49, 7 squared is also 49. Again, I think I've mentioned this before, but if I have not, then please pay attention. There's nothing wrong. X will be plus minus 7. There's nothing wrong in square rooting it that way. X will be plus minus 7 because negative 7 squared is also 49. Positive 7 squared is also 49. What's risky is actually the process of squaring both sides itself. Because for x squared equals to 49, plus minus 7 is the answer. But we only wanted 7. So squaring both sides is a slightly risky part. So just make sure you cross-check your answers at the end for squaring both sides. Okay. And for this one, don't panic if you get 1 equals to negative 5. It might happen. Okay. There are other methods as well, but we can't. There's this one graphical method that's actually really reliable, but we can't get into so many methods. And that graphical method is slightly tricky. Okay. So most books use this. Okay. And most mark schemes use this also. Of course, any method is recognized, but you could stick with either of these two methods. Okay. Now, the second one is modulus inequalities. So suppose you have something like modulus of x is lesser than p. Okay, p is just any number. How this works, if you remove the modulus, will be x is greater than p, sorry, lesser than p or lesser than negative p. This is what happens when you open the modulus. Okay. Now, why is that? There are two reasons. Okay, there are two reasons. Let me draw the graph of modulus x for you. Notice the left-hand side and right-hand side are reflections across the y-axis. The left-hand side and right-hand side are reflections across the y-axis. Now you might be thinking, Shamet, I thought that there were supposed to be reflections across the x-axis. Yes, but the negative part of modulus of x, of x. For example, this is y is equal to modulus of x, right? Suppose it was y is equal to x. Y is equal to x would be something like this. I'm drawing it in dotted because it's not part of the modulus. The dotted and the reflected part are across the x-axis. Okay, so y is equal to x and y is equal to modulus x. Those parts are reflected across the x-axis. Okay, but in this case, in the blue graph, the left-hand side and the right-hand side are reflections across the y-axis. Okay, so I hope that you understood that part. So if you have modulus x is lesser than p, so suppose p is any, so suppose y is equal to p. Suppose it's a straight, y is equal to p will be a straight line. Okay, if p doesn't have x, so p is a constant, right? Y is equal to 2 is a straight horizontal line. So y is equal to p is a straight horizontal line. Okay, now you want to find where p is greater than modulus of x. Where p is greater than modulus of x. Okay, so let's see how this can be done. Have we made a mistake? Have we made a mistake anywhere? I feel we have made a mistake, or either I'm feeling too sick to explain this because of my health recently. Let me just check if am I doing everything correct. I seem to be doing everything correctly. Okay, 1 second. Let me think about this. Okay, if you're if you're watching it on YouTube, let's just skip forward a few seconds. Let me think about this. Okay, okay, guys, understood. Okay, I understood. I think this was what confusing me. Instead of x, but I use fx here. Okay, I think just the case of x alone might be confusing. Use fx here also. So you want the points for which it's lesser than, which modulus of fx is lesser than p. So for which the blue line is lesser than p. Now, the blue line is lesser than p in all these situations. And this is just a reflection, so I'll just draw it this way. So we need to find this x value here. This x value and this x value. But here's the thing I have for you. If this x value is a, this will be negative a because of the reflection. Because this point and this point, well, they're on the same line, there will be reflections across the y-axis, right? So if this one has 5, this one will be -5. So both of them will have the same value. Now you want to find what the value of a actually is. What the value of a actually is. What's the value of a going to be? The value of a is going to be fx equals to a, right? You use fx and you equate it to a. Fx is the blue graph, you equate it to a. Sorry, fx equals to p. My bad. Fx equals to p. You do fx equals to p, then the value of x you get will be a because you're trying to find where fx intersects with p. Fx intersects with p, not modulus of fx, yeah? Not modulus of fx, just fx. Just fx equals to p. Means this yellow line and this blue line. So you'll only get a. If you try solving this directly, then you'll get negative a also. But that's another modulus there. So fx equals to p, okay? Fx equals to p, you get x equals to a. And because it's a reflection, this other part you can already know. You already know a, that means you already know negative a as well. And here you can see it's between a and negative a. Okay, so what you could do is you could do fx lesser than p or negative p. Because you want to remember, I'm doing fx equals to p here. So here I'll do fx lesser than p or fx greater than negative p. Now you're like, sure, it should be between a and negative a, right? Now how p and negative p? X should be between a and negative a. X should be between a and negative a. Fx should be between p and negative p. And when you solve this inequality, then you're trying to find a basically. The only difference is instead of an equal, you have a greater than and greater than sign. So it's doing the same thing. It's doing two things at one time. Or you could just do this way. You can find a first, and then you could do this directly. But you could do it this way also because it's essentially the same thing. When you solve this, you're finding a only. Okay, so that's one method. That's the logic behind it. Okay, but please just memorize this result. I want you to memorize this result. Okay. One more way you can think about it, and you could use this if you forgot the formula. Okay, if you forgot the formula, fx could either have been positive or negative. So suppose fx was positive, it would be fx lesser than p, or suppose fx was negative, it would be negative fx lesser than p. So if I remove the negative here, it will become fx greater than negative p. Remember, when you do negative, the sign changes. So you have this and this, which is actually just fx between p and negative p. Okay, that's the formula for you. You can do the same thing if it was fx is greater than p. If it's fx is greater than p, okay? And even for the graph, if it's greater than p, it'll be more than a and less than negative a. X will be more than a and less than negative a. So fx will be more than p and less than negative p. Okay, so you could do the same results for a different inequality symbol. And by the way, if this was equals to, it means a can also be an answer. So this will be equals to equals to. If this is just without the equals to, this will be without the equals to, without the equals to, without the equals to, without the equals to. Okay, I hope that makes sense. So now the second one was if it's something like modulus of fx greater than p. So you can use these same results, either the first method or the second method to prove it. I've orally proved it to you in a way. It'll be fx greater than p and fx lesser than negative p. Fx greater than p, fx lesser than negative p. Okay, I hope that's clear. Now, there's another case. And by the way, in these cases, avoid squaring both sides. Okay, avoid squaring both sides because of the reason I've told you. Avoid squaring both sides. Okay, there is another case where you have modulus inequality. So modulus fx is greater or equal to modulus of gx, suppose. Again, just square both sides. Just square both sides, but this inequality will remain. Okay, it won't be equals to, the inequality will remain. The inequality will remain. And in this case, squaring both sides is probably the best option. Okay, you'll be like, Shamit, over here, you had two options. For if it's equals to, you had two options. One was squaring both sides, and one was the case by case. So in this case, why can't we do it case by case? You want to do case by case? Okay. See, assume it's positive and positive. It will be fx greater or equal to gx. If it's positive and negative, it will be fx greater or equal to negative gx. If it's negative and positive, it will be negative fx greater or equal to gx. If it's negative and negative, it will be negative fx greater or equal to negative gx. If they were equals to, if they were equal, then this and this were the same. Remember, if they were equal, then this is the same and this is the same. But in inequality, they are not the same. Okay, because this thing is actually, if you suppose you want to switch this negative here, this will actually be negative fx lesser equals to gx, because the inequality, the sign flips. The inequality, the sign flips. So these two things aren't the same anymore, huh? The sign is different already. These two things aren't the same anymore, huh? And in this case, let's say, how will you do that? I suggest you don't, instead of multiplying the negative, you add fx on the other side and add gx on the other side, because there are two negatives here, so it might be confusing. It'll become gx is greater or equals to fx. I just took gx here by addition and took fx here by addition. Okay, two negatives, it would have gotten confusing. Okay, so yeah, in these cases there are four different situations, and some situations might not even be accepted because of many complications. Okay, so in this case, just square both sides. Okay, but again, just be careful when you're squaring both sides. Okay, be careful when you're squaring both sides because of the reasons I've told you earlier. Okay, so I hope that part was clear. Now, let's move on into sketching cubic graphs and their modulus. Sketching cubic graphs and their modulus. Okay, suppose you have a graph which is y is equal to x minus 3 times x minus 2 and x plus 1, suppose. Okay, for a graph, there are always three things you need to know: x-intercept, y-intercept, and turning point. Turning point means what? Like a quadratic graph has a thing here, that's turning point. Okay, so cubic graph will also have turning points, but you don't need to know turning points for when you're drawing it. You don't need to know the turning points when you're drawing it, because the method you find it, you learn it way later. Okay, so you don't need to know the coordinates of the turning point. You don't need to know that. Okay, so only x-intercept and y-intercept. So what's the x-intercept when y is equal to 0, right? So it will be x minus 3, x minus 2, x plus 1 equals to 0. So you can do it case by case. It will be x equals to 3, x equals to 2, and x equals to negative 1. The reason is because when either of them is 0, the whole thing becomes 0. So if x equals to 3, this thing is 0. Doesn't matter if this is 3 minus 2 positive 1. Doesn't matter if this is 3 plus 1 4. This is 0. Whole thing is 0. Done. So x equals to 3, 2, and negative 1 are your x-intercepts. Now, means you have coordinate 3, 0, 2, 0, negative 1, 0. Now you have y-intercept. Y-intercept is when x equals to 0. So this is 0, this is 0, this is 0. Negative 3 times negative 2 times 1. So y-intercept equals to 6. So you have 0, 6. So then you can draw a graph. Okay. Dun, 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 dun. It seems like this cubic graph will look like this. Okay, this is how cubic graphs work. Cubic graphs either have a shape like this or have a shape like this. Okay, because they usually have 3 x-intercepts and one y-intercept. So they'll have 2 turning points usually. Okay, so in this case, this will be -1, this will be 2, this will be 3, this will be 6. Okay, and positive cubic graphs have a shape like this. Negative cubic graphs have a shape like this. So positive cubic graphs, right, at the end they tend to go to positive. At the end they tend to go to the positive axis, and negative cubic graphs at the end they tend to go to the they always positive cubic graphs at the end they go to the positive y-axis. Negative cubic graphs at the end they go to the negative y-axis. Like quadratics, positive are like this and negative are like this, right? So positive cubics are like this, negative cubics are like this. Okay, how do you know if it's a positive cubic or not? Just look at the coefficient of x cube. Like how if it's positive x squared, it's a positive quadratic, negative x squared, it's a negative quadratic. So if it's positive x cube, it's a positive cubic. How do you know if it's a positive cubic? Just find the coefficient of x cube. This will be x times x times x. That's x cube already. Suppose there was a negative here. It will be negative x times x times x, negative x cube. So that will be something like this. Okay, that will be something like this. Now, what if they ask you for the modulus of this graph? What if they ask you for the modulus of this graph? Then the modulus of this graph will just have the negative part reflected. So like this and like this. Okay, the modulus of this graph will just have the negative part reflected upwards. Now, sometimes the cubic graphs might be a little bit, they might just add one more thing here. They might say it's 2 times x minus 3 times x minus 2 times x plus 1. Okay, the only thing which has changed is the y-intercept. Because x-intercept will stay the same. X-intercept will stay the same. X-intercept is what? When y is equal to 0. So it will be 2 times x minus 3 times x minus 2 times x plus 1 equals to 0. This 2 just cancels out because it just dies there in the division. So your x-intercepts are the same. But for your y-intercept, when x is equal to 0, this is 0, 0, 0. It will be -3 times -2 times 1 times 2. So your y-intercept becomes 12 actually. That's and because of that, the stretchiness, the slope of your graph at different points changes slightly. Okay, and yeah, similarly with the modulus, it will change slightly. Okay, so I hope that part is clear. And remember, this part and this part, they'll have the same x coordinate but different y coordinate. So this is a, this is negative a, because these are reflections across the x-axis. Reflections across the x-axis, the y coordinates becomes positive and negative. The x coordinate is the same. The y coordinate from a became negative a. If it's reflection across the x-axis, the y coordinate becomes goes through the positive negative thing. If it's reflection across the y-axis, the y stays the same and the x coordinate goes across the positive negative thing. Like in this case, the x coordinate went through this a negative a thing, right? The y coordinate stays the same, p. So in this case, the x coordinate stays the same, whatever value this is. Okay. Yeah. And sometimes they might ask you to solve inequalities using cubic equations, but for that, they will give you the graph. They will give you the graph for inequalities using cubic equations. So suppose they want to ask you, let me erase the modulus one, okay? I hope you already knew that. Let me erase the modulus one. Why? Because I want to ask you a question without the modulus one. My choice. Okay, now tell me x minus 3, x minus 2, and x plus 1 is greater than 0. Means, by the way, if they ask you such a question like this, most probably they'll ask you to draw a graph in part 1. So this is a part 2, most probably. Okay, so then you can use your graph in part 1. They're asking for which is greater than 0. So it will be greater than 0 will only be this point. This side is greater than 0 and here. So it means after 3 and between 2 and -1. Remember, greater than 0, so not greater or equal to. So you can't include this point. So I'm going to draw it like a circle there. So you can't include those points. Okay, so it will be greater than 3, not greater equals to 3. So it will be x greater than 3 and between 2 and -1. You can cross check, choose any value. Choose any value greater than 3. Let's say we choose 5. This is just a matter of trial and error cross-checking. If this is true, let's say x equals to 5. Is this thing going to be positive? Yes. 5 minus 3 is 2. 2, 3, 6. 2 times 3 times 6 is 36, which is positive. Yes. And let's see. So if x must be greater than 3. So if means x is equal to 2, suppose, or let's say x equals to 2.5. 2.5 doesn't fit. 2.5 doesn't fit here. Doesn't fit here. These are the conditions we got for it to be positive, right? It doesn't fit here. It doesn't fit here. It means at 2.5 it should be negative. Let's see. This will be negative 0.5. This will be positive 0.5. This will be 3.5. Yeah, this is negative because one negative is already there. See, yeah. So this is a way of cross-checking our answer. Let's say if this is correct. Let's pick a value between -1 and 2. Let's pick 0. This becomes -3 times -2 times 1. This is positive 6. Yeah, it works. It works. So this can be a quick method for you to cross-check. Okay. They might ask you inequalities with a modulus also. Okay. So that's so just practice as many questions as you can. Now I want to ask you a question with a modulus. Okay, so I'll just draw this part again. Okay, the question is, and this is a common question. This is a common one marker. Okay, find the values of k. This is a common one marker for which y equals to k has exactly 4 solutions. Or I have a better idea, exactly 3 solutions. For 4 solutions, it will probably require you to use calculus, and we don't want to go there yet. Okay. Y is equal to k has 3 solutions. Y is equal to k. K is a horizontal line. K is a horizontal line. So it could be something like this. It could be something like this, something like this, something like this, something like this. They wanted to have 3 solutions. And I'm talking about the modulus graph only. Okay. So let's erase this part. Y is equal to k has 3 solutions. So means I draw horizontal line, it should have 3 solutions to this graph. Means it should have 3 intersections. Okay. Remember, I've told you many times that if you want to find the solutions of an equation, at that point the graphs intersect because the x and y values are the same. So suppose the value is here. It's only one intersection here, one intersection here. It's at this point specifically, that I have 3 solutions. One here, one here, one here. At this point, suppose I'll have 4 solutions. No, I'll have many. I'll have 1, 2, 3, 4, 5, 6. I'll have 6 solutions also maybe. Okay, I might even have 6 solutions. But they usually ask this type of for quadratics, but they might ask you for cubics as well. So for 3 solutions, I have only a line here. 1, 2, 3. Or this. This part also works. This 1, 2, 3. So it'll be y is equal to 6 and y is equal to 0. Y equals to 6 and y equals to 6 and y equals to 0. Anywhere else, does it have 3 solutions? See, over here, it always has more than 3 solutions. Okay. If it's like this, it has already 1, 2, 3, 4, 5, 6 solutions. If it's something like this, then you'll have 1, 2, 3, 4, 5 solutions. If it's at the highest point here, then instead of like this, it will be only 1 here. Okay. But then if the question requires you to know this point, then you'll need to know differentiation, which you'll learn later. Okay. So for cubics, it's very unlikely that they'll ask you a question which you'll need to know this point. Okay. But this point, okay, no, this is just a y-intercept. This is just a y-intercept. Okay. And this is just a sketch, assuming my sketch is correct. My sketch might be wrong. Maybe the graph is a little bit more like this instead of like this. Maybe the graph is a little bit more like this. So this is just an example. It's not always that the y-intercept will be the point like that. Okay. It depends from graph to graph. Your graph must be very accurate. And this was just a sketch. But again, most probably they won't ask you that much detail for cubic graphs in this y is equal to k thing. They definitely good chance of this coming out. Okay, this one usually comes up for quadratics. I don't recall exactly, but for quadratics it has for quadratics it's definitely come out. I don't recall if it's come out for cubics, but if it does, just making you prepared. Okay, now just one last concept we have to cover. These are slightly complicated equations. which look like a which look very complicated, but it's actually just a quadratic equation. So suppose I have 4x to the power 4 minus 17x squared plus 4 equals 0. Now you'll be like, what on earth is this? It's very simple. Okay, there's this idea called substitution. So you can let s equals to x squared. S equals to x squared. Why does that work? S equals to x squared works because now, and why did I choose S? S is just any letter. Okay, you could choose let P equals to x squared. I'm choosing S because my name is Shamit and because we are Shamo, so I'm choosing S equals to x squared. So if you notice, if S equals to x squared, S squared will be x power 4. This is x power 4 here. So I can actually write it as 4s squared minus 17s plus 4 equals to 0. I can write it like this. Now this is just factorable into 4s s minus 1 minus 4. Yeah. So that means s equals to 1 over 4. S equals to positive 4. S was actually x squared. S was actually x squared. So that means x squared equals to 1 over 4 and x squared equals to 4. Then you can do x equals to plus minus 2, x equals to plus minus 1 over 2. Okay. Or if you guys are pretty OP, there's this thing you can do also. You can directly do it like this. If you can. Okay. Like how for quadratics, you can do it directly like this, right? So for this is almost like a quadratic, you can do it directly like this. Now suppose this was 4x to the power 6, 17x to the power 3, then you can let s equals to x cubed. Okay. Now you'll be like, Shamit, what if it was 4x to the power 4 minus 17x cubed plus 8x squared? Now what can you use as p? Because there's the x cube also here. Suppose there was an x cube term here. They won't ask you that. Those questions you can't solve right now. Okay, they won't ask you all that, so don't worry. Okay, there's one more variation of this. There's one more variation of this when it comes to an exponential question. So I have a question for you guys. 2 to the power 2x minus 6 times 2 to the power x plus 8 equals to 0. Okay, in this also you can do it. In this case, you can let s equals to 2 to the power x. Now you'll be like, okay, Shama, this will be s. So it becomes, this will be minus 6s. But how do you, what do you do with this? This is 2 to the power 2x. This is 2 to the power x. Notice s squared will actually be 2 to the power x squared, which is 2 to the power 2x. Indices, law of indices, okay? If you don't know, I've made a video on that also. But if you forgot, just reminding you, if it's in this case, the x and the 2 multiply. So it becomes 2 to the power 2x. So this is actually just s squared minus 6s plus 8 equals to 0. So this becomes factor. Minus 4 minus 2, s minus 4, s minus 2 equals to 0. So it becomes s equals to 2, s equals to 4. S was what? 2 to the power x. So 2 to the power x equals to 2, 2 to the power x equals to 4. So x equals to 1 and x equals to 2. These are your answers. Sometimes you might be given weird values. Instead of 2, maybe they give you 3. 2 to the power x equals to 3. That might be how the question is designed. In this case, you'll need something on logarithms, which is a later chapter, which we'll do. Okay. Most probably the next video I'm going to be uploading is going to be on logarithms itself. Okay. So for that, it's going to be x equals to log base to 3. Okay. But for this chapter, if you're practicing, then the questions are quite well designed. So like how I got 1 and 2. Okay. Yeah, that's it, guys, for this video. 35 minutes. I would say I'm quite, I did quite well to manage the time and quality. Okay. So I hope you guys enjoyed this. I hope you got good value from it. Okay. Keep studying, keep enjoying, keep having fun. Peace out. See you.